Alright, welcome to some new slides. So because there is a holiday on Monday of this week, there will be only one lecture because I want to keep us in sync with my in-person class that is Monday, Wednesday. So just one lecture this week. It'll be this one. We're going to start learning about functions. Yay! So let's get right on into it. I have a feeling that you think this. We have been writing longer programs, and that has made our main functions get super long because that's the only place that we have been able so far to write code, right? It's always int main with some optional stuff for maybe command line arguments, and then you have your braces, and then you have a bunch of code, right, that you've been writing now, a lot, and usually it returns 0 at the very end, right? And then your closing brace. All of this stuff is just a lot, right? Functions, our main function is getting quite long. So let's see if we can fix that. It would be nice if we could maybe take this, put it in its own function. Take this, put it in its own function. Same with this. Then we'll have a 4-line main function, yeah? That is the goal. Alright, so let's make our own functions. That's what we would like to do. And then we could hand off the work to those other functions. Like main can call maybe function 1, who will itself call maybe inside of it function 2 and function 3. They'll do their own little work. And maybe function 3 needs function 4's help, so it'll call it like that. This is the kind of process that we want to have. Right now we're doing this with library functions, but we can make our own functions to encapsulate behavior, alright? And make our main functions look a little bit cleaner, okay? So that's what we'd like to have. Here's how you do it. So you secretly already know how to write functions because you have been making a main function this whole time. The same style is followed with any others. So let me show you what's going on here. What you need, the pieces, to create your own functions. Okay? So the first piece is called the return type. You have to give back a value sometimes, and you have to say what kind of value you're going to give back. So main returns numbers, integers. So its return type is int. So return type, that is 1. Okay? Main returns integers like 0. That is the first thing you say when you are creating a function. And then, of course, you give it its name. This would be number 2. Of course, this function is called main. It's forced to be called that. And then it might need to be called with some stuff. That's 3. Here is the stuff. They're called parameters, right? So this, argc and argv, whoever's calling main, I guess it's the terminal, right, who's giving us our command line arguments, that is where you put this information, like what you're getting from the person who calls you. And that's where the parameters go. And then, of course, you implement. You give the body of your function what you want to get done when it gets run. And for functions that return things, they have a return type like int or double. They need to give an int back or a double back. You give things back in return statements. That's here's an example of one, right? Return 0, give something back to whoever called you. In main's case, it's like saying 0 to the terminal, like, hey, I ran properly, I finished correctly. And return statements are part of the body. Okay, so all this stuff you've been seeing already, now hopefully it's all going to come together. Okay, so let's have the world's simplest function, I guess, first. Let's write our own function to add 2 integers together. It's just going to give back their sum, because why not? So here's what it's going to look like, with some braces, of course. Int, because it's going to add 2 integers, x and y, and it's called add. Okay? Takes 2 numbers, gives back their sum. That's what we'd like to do. Okay? So let me show you how we're going to call this. Somebody's going to say add with 2 numbers, 42 and 43, or a and b, doesn't really matter. And what this is saying, we maybe haven't thought about this when we were calling library functions, is it's asking so nicely from C++ to please run the function, go straight to the function's definition, run the function called add with, well, we're using x and y in the definition, with x being set to a, so that's the first thing, and y being set to b. That's the second thing. These can be anything. They're just variable names, but they're your parameters. Okay? So let me show you this. Let's make an add function. So I'd like to be able to do stuff like this. See out the result of adding 42 and 43. So here's how I will declare and define a function called add. It gives back, well, it's called add. It takes two numbers. We'll call them x and y. That will be filled in with whatever we pass along, right? It's going to return an integer. It gives back the answer. That is an integer, right? It gives back the sum. And then we give the body, let's just return x plus y. Okay, so that's our add function. Whenever we call it, we get plopped straight here with these parameter values being set to the argument values. So 42 and 43 are going to be x and y, and then we return back their sum, which allows us to print it, because we're given the whole result to see out, right? Yay, so we get 85 back as the answer, and that is beautiful. So we just ran our first function. So this is the add function with ints. It adds two ints and gives you back a third. You can what's called overload a function, because you might want to add doubles, you might want to add strings. You could have a bunch of functions all called add. That's totally fine as far as C++ is concerned. Some other languages don't like that, but C++ is happy. So let's make an add function on doubles, and eventually on strings, so let me just right now include string. So instead of ints, let's do doubles. So now we have an add function, same name, but now it takes a double x and y and returns their sum. These values can be anything, they're just variables, so we're calling our parameters a and b now, so we'll return a plus b. No big deal, okay? Same with, now it's a and b, I guess. And I can also add together strings, right? That just concatenates them, it brings them together, so let's replace with string. Oh no, there we go. So it's doing the same work. You see that? Oh, and oops, I have to call this b. There we go. So, same function, 3 different times, different types though. So here's the add that takes two strings, x and y, and gives back a new string that is them with all their characters right next to each other. So, I don't know, see out add 42.5 with 43.75, that'll call the double add function. It just knows because we gave it the different types. And then, I don't know, string A is I, string B is mom. I guess I only need one space, let's put it there. And I can see out adding together A and B. Won't that be nice? So that is add on strings as well. So 3 different adds, each doing plus in their own little way. Okay, it knows to call the right one given the types that it sees. C++ can choose the proper add function based on the types that you're giving as arguments. So that is how to make your own simple function. Isn't that neat? So we did that. Let's do more. Let's have a different kind of function. Let's have a function that just prints to the screen hello, okay? And so it's not going to take any parameters, it doesn't need anything, we just want it when it's called, please print hello, so it's going to be empty stuff inside of those parentheses, just like int main is usually for us. And then, because it's not going to give back an answer, it just does stuff, we're going to use the special keyword void for the return type. It's not a type in C++, it's just a keyword that means I'm not giving anything back, okay? Void is for when we give back nothing. There is no return needed in our function. A void function just goes and does something, okay? So that is how that's going to work. So let's have a hello printing function. So I just want to call it like this, print hello. Just like that. So it's void, name of the function, no parameters, it just does something. Okay. So when this gets called, it's going to jump here, run this code, and come back. And I can call this same function as many times as I want to. I also said that in the slide, so let me make sure to say that too. Wee says hello once, but I can always, that's the point of functions, right? I can call the same function as many times as I want to. I don't have to repeat myself. It just always knows to go up here and run the code. Okay? Notice what I'm not doing. I'm not saying something like, see out the result of print hello. That's not making any sense at all, right? This is just a function that's meant to do something for me. It doesn't give back a value that I then go and print. It does the printing itself. So you see how it's not giving back any value? It is just doing something. That's the difference between like a string return type or an int return type and a void return type. Okay, I hope that makes sense. Please yell at me if it does not. So that's print hello. Yeah, and I showed you this as well. Let's go back, because we learned how to call library functions, but now we know a bunch of more terms, right? So let's go over those terms some more. So when you're calling a function, what are you doing? Like, let's say we're calling the add function. Up here, let me give the declaration of that function. Int add, int x, and int y. So that's how the function was created, and we want to call that function in this line. All right. So to call a function, you need to say which one you're calling. So you got to give its name as usual, and then in the definition, we call it parameters. These are the variables that get set to whatever you pass along. The things that you pass along, remember, are called not parameters, but arguments. And I mix these up all the time. Don't worry, you will too, but this is the proper terminology. Okay, so A and B in this case, in the call, are called arguments. They're what we want to use to replace the values of the parameters when we call the function this time. Okay, so the idea is A is going to get to be x, B is going to get to be y, and then it's going to run the body of the add function with that being set like that. Okay, that's how that's working. So I'll get back to that. Then finally, if the function call gives back something, and it does in this case, it's going to return an answer, then we need to use that answer usually, right? You can't just call this function with a semicolon and expect anything to happen. It's just going to compute the value, and then it gets returned and goes off into the ether, right? So we have to do something with the value that's given back to us. So here is an example of assigning the value to a variable. Maybe alternatively, we could have just gone and straight printed it out like I was doing in code, but you got to use the return value if there is one. It's not just automatically printing or anything. And then, yeah, the idea is the parameters in the definition receive the values that you're using when you make the call to that function. Okay, that's what's going on. X gets set to A, Y gets set to B, and then it goes off and runs the body of the add function. Okay, that is how you call a function, though you know how, all over again, now that we know more terminology. Okay, so with that, I'd like you to try something. So take a look at this example and see if you can figure out what's wrong. There is something wrong with the code. See if you can figure out what. Don't worry about the Google Docs because this is an asynchronous class, but think about it. Maybe write it down if you like to. See if you can fix it even. So, what do you see? All right. So here's my function. Int main. It's trying to print the result of calling the 5 function by and multiplying that by 2, whatever that is, prints it out, new line. Okay, and then the 5 function, it's printing 5. Interesting. So, did you see the problem there? What's the issue? This function just prints 5. It prints 5 to the screen whenever it gets run. It does not give back the answer 5. It's a void function. You see that? This you might think gets replaced with 5, but no, this function gives nothing back. There is nothing that's being replaced. It makes no sense to multiply nothing, because it's giving back nothing, by 2. So here's kind of what would happen if this were allowed to compile. You call, we're running this line, and what it does is it needs to compute this answer so that it can give it to cout. So it goes off and it calls 5, which prints 5, and then gives back nothing. And then it tries to multiply nothing by 2, and then prints that. There's what would happen there if it were allowed to compile. My guess is as good as yours. So just notice that printing has nothing to do with returning. There's a huge, huge difference. Printing gives nothing back, and so this kind of computation makes no sense at all. This just prints 5. It doesn't give back 5, so we can't use an answer. There is no answer. So if you wanted to get back 5 here so that you can multiply it by 2, you have to return it. It needs to be int 5 or something. It has to have a return type of int, first of all, if you want to give back a 5. And then you have to say something like return 5, which would not print anything. It would just give the number back to whoever called you so that it could be printed. Okay? So that is the key difference. So think about that some more. There's a lot to say here, and so I have another slide just on this, but I wanted to get you used to noticing that difference, because this is a very common error when you're starting to learn functions. You think that printing always gives back a value and can stand for the function call, and that's not true. Okay, so let me show you this. Return versus print. All right. The question is always, and I want you to think of it this way, how can you use these two functions in main? What's the difference between them? Okay? How can you use add? Well, it's always in some bigger computation, right? Because add gives back a value. It's something like you call add with 3 and 4, and then maybe you'll add 2 to that, something like this. Some large expression, that's fine to use add with, because it gives back an answer. You can give that to C, because when you call a function that gives back an answer, it gets replaced with its return value. Okay? And so really, C++, once it runs this, it sees 7 plus 2, and then it calculates 9 and puts 9 in C, things like that. Same with using cout. You can give the result of add to cout, 5, 6 this time, because you get to assume that that call is getting replaced with its return value. And so this will calculate, it goes off and calls add, it will calculate 11, and give 11 to cout, and it will print it. And that's totally fine, because it gives back a value through return. Okay? Print hello is another story. You see that you are only allowed to call print hello like this. Print hello, parenthesis, parenthesis, of course, and then a semicolon. This is the only way you're allowed to call this function, because it does not give back a value. It just goes straight to this body, runs it, gives back nothing. Okay? So you can't do something like this. Cout the result of calling print hello. Because this is gonna, in the call, print hello, and then you expect it to give something back so that you can print that too? That makes no sense. Okay? So this is not allowed, and I hope with enough examples, with enough of me drilling it into your mind, you'll notice it. But this does not make sense, okay? So let me show you that in code just briefly. Print versus return. .cpp. Let's copy this print hello code, and we will also copy, we'll take this, and yes, it still makes no sense, but here's what you get back. Oh shoot, okay, yeah, it depends on the compiler, but it looks like it is allowing, oh, because I'm not, never mind, I'm compiling the wrong file. I was very confused for a second. Thank goodness. Okay, so it definitely doesn't compile. That makes me happy. And what's the main issue that it says here? There's plenty of outputs. So it's like, cannot match void with any type that I know how to print. That's what it's saying. It's like, I don't know how to print a void, because void means nothing. Okay? That is the problem, and that is why you can't do that. It just, you call it and it does something for you, okay? So that makes no sense. And if I go to my add function, here's how we use our add function, right? We say cout add 23 new line, because this is getting replaced with the call and its result, and this will print our 5. Oh shoot, darn, I put this in the wrong file. What's the best way to fix all this? Let's move it all to print versus return. I'll take this, put it here, and I'll take this, save that, and put it here. Okay, that's better. So, not print hello, print versus return. It looks like I forgot to save it. There we go. Okay. Now I'm happy. Prints are 5. On the flip side, it also makes no sense to do this for add 3-4. Because it's computing 7 and then you're not doing anything with it. You see that? There's no printing. It's just, okay, it makes 7. 7 goes away. Because you're not using the return value. Okay, so there's 2 different ways to go wrong. One way just doesn't even compile. The other way is just you're doing work for nothing. Okay? So hopefully that clears things up a bit more. Return versus print. All right. So that is the end of the intro to functions. Now I just want to talk about using them to do cool stuff. Let's talk about breaking down problems into smaller pieces. Okay? So here is an example little problem that could be fixed or could be solved by doing this process of breaking down a problem, okay, into smaller individual pieces, right? So here's my problem that I'm giving you. So I want you to sum the squares of all the numbers between 1 and n for some n that I give you, okay? So maybe the user types in the n, and then it's your job to calculate the sum of all the squares of all those numbers from 1 to n. So for example, if the user types 3, n is 3, if n is 3, then I want you to sum all the numbers, all the squares of the numbers between 1 and 3. Yeah, so sum 1 squared plus 2 squared plus 3 squared. Whatever that is. That's 1 plus 4 plus 9 equals 14. So that's what I want you to calculate for arbitrary values of n. Okay? It should always work. And so this is a slightly complicated process, and it would benefit from being broken down into smaller pieces, potentially functions. Okay? So the question is, how can I do it? Okay, I'll make an algorithm. How do we do that? Okay, let's keep going. So remember what an algorithm is, right? It's just a sequence of steps to break down a problem into smaller pieces, okay? To solve a problem. And sometimes that does involve this process, okay? So, yeah, really, besides thinking computationally, I want you to learn how to break big problems down into smaller pieces, because then they are solvable. They're not as big and scary looking once you start breaking them down, okay? So, essentially, I want you to learn how to make a bunch of little algorithms for yourself that can be combined into the big piece that is eventually solvable, okay? Hopefully that makes sense. Because then, once you know that, okay, I gotta do this first, then this needs to happen after that, and then I can go either here or here based on this answer, programs make a bit more sense at that point. It's not just, okay, how do I do the whole thing? It's how do I do this first step? How do I get it ready for this second step? What should I be branching based on? And what are the contents of those branches? It all gets a bit easier, okay? That's the idea, and that's when you start breaking down those problems. Because I want to stop giving you, the whole point is, I want to stop giving you the answer. I don't want to tell you what to do anymore. I don't want to give you as detailed of fix-me's in your labs, okay? I want you to come up with the strategy. That's where I want to get you in this class, okay? Because that's what it means to be a programmer. So here's the process, essentially, that I want you to follow, or that you will learn to follow. So you're going to get a problem always. There's always something that you're trying to do. You need to figure out what is going on with it, like how does it take its input, because usually it takes input from the user, right? That's how most programs work. And how does it create the output? How should it create the output that it gives back to the user, right? Because most programs print things. They don't just do a bunch of work and then end, right? So that is essentially the programming process. And once you've got something compiling and running, it's your job to start testing it, right? Test it, debug it until it does the right thing in all the cases, yeah? And what is debugging but printing a bunch of answers at intermediate stages of your program? So that is another thing that we will do, okay? So that's essentially the process that I want you to get you in the habit of doing. So let's do it for this example, okay? So I want to sum the squares of all the numbers from 1 to n. That seems like large and scary, but it's really not too bad. The first thing we want to think about are what are the pieces involved in this process? Do you see them? Think about them in your mind. Take just a second to think about that while I get some water. And if you stare at this long enough, you'll see, okay, I need to calculate the sum of something. So that's one piece. I need to square some things. That's another piece. I need to generate the numbers from 1 to n. Do you see how there are 3 pieces, 3 main steps involved in this program to solve the problem? That's the key, okay? And then I want you to track the flow of data, which will tell you what needs to be done before what the other things, okay? Like what needs to happen in what order. So you need to sum the squares of these numbers, which means you need to start here, right? This needs to be step 1. If I don't have the numbers, then I definitely can't sum anything. I can't take their squares. I can't do anything. So I need this first. Need this first. Do you see that? So even though the problem statement is in this order, you need the last thing that's talked about first. And then you give all these numbers to like a squaring function. That's step 2. Because the very last answer is the sum of all of them, right? That's got to be step 3. Do you see that? That's how the data is going to flow. You generate all these numbers, you square each of them, and then you sum them all together. You see that idea? That is breaking down a problem. That is the key. Okay? So, we're going to implement this. We're going to solve this problem, and I want to teach you a strategy, a way of getting started, even if, like, usually the problem's a bit harder than this. If you're not sure of what to do, but at least you know about the pieces, here's a good way to start. Okay, I want you to get in the habit of doing this. It's writing a bunch of things called stubs before you actually start writing the code, just to get something compiling, okay? Something compiling and ready to go, okay? That's what I want you to be able to do. So let me show you what a stub is. A stub is just when you make a function that gives back just a dummy answer. If it's supposed to return an int, just return 42 always. Like, don't give back the real answer yet. Just give something back that is the right type so that the function will compile, so that you know, like, you have your scaffold ready to go, okay? So let's do this for our sum of squares problem. And we'll call our function sum squares from 1 to, okay? Oops, I want to make a new file called that. So I guess the idea is I have cout enter a number, get it, and then we're going to say cout sum squares from 1 to n. Yeah? And so here's what a stub looks like. The sum is always going to be an integer if you're given an integer. Here is a stub. Return 42, no matter the number. See how that's a stub? That just gives back a dummy answer to make sure what we're trying to do here always is working. So that's a good way to get started, just to know that you have a program that compiles before you go any further, okay? Because sometimes, like, that is not yet correct. And it's hard to write a correct program if just the scaffolding doesn't even compile, okay? So 3. Sum of all the numbers squares between 1 and 3 is 42. The sum of all the squares between 1 and 100 is 42. Just always gives back 42 right now because it's a stub. But it compiles and it runs, which lets us get ready to do the real work. Okay? So that's a stub. Let's now do the real thing. Let's write the actual implementation for the sum of squares from 1 to 2. Okay? And remember the processes. We need to enumerate between 1 and n, right? Which is going to involve a loop. We have to try all the values. And so we'll put that loop inside of our function, and then we're almost there. Okay? We also need some other helper functions, don't we? We need to be able to square numbers, because that's part of the strategy. We need to square numbers. We can call this inside of this function, and then let's just be silly and not use plus, but we'll use the add function that we made before because we're so proud of it. Okay? So by breaking down these steps into different functions, it makes it easier for us to think about the problem as a human. Okay? We're not a computer. We don't have a ton of memory to keep stuff in our brain, like tons of code in our brain all at once. That is unhelpful. Okay? So here is kind of the strategy. So I need to iterate from 1 to n right now. So there's a loop that goes between 1 and n. Yeah? And then I just need to, for each I, right, I need to square it, square I, and then I need to keep track of the sum of all those squares, so sum equals 0. Here is int I squared. I need to set sum to be, and remember I'm using the add function instead of the plus operator, so I'll say sum equals add whatever it was with I squared. Look at that. Isn't that cute? That is, and then return the sum. Return the answer once we're done computing it. Do you see how this becomes a nice short function? Now that I don't have to worry about doing all the intermediate things, I'll do those in a different function, right? So let's do int square. It takes some number and returns its square. That's easier to think about when I just say square of I. Like, I can assume as the programmer it's going to get the right answer, and I can worry about computing that right answer somewhere else. Yeah? That's the goal. And then we'll do the same for add, which we already have up here, so I'll steal that just to save time. Okay? So here's square. Returns the square of a number. Here's add, sums together each number, and here is sum squares from 1 to 2, which goes through all the numbers between 1 and n, squares them, adds them into our sum, and hopefully gives back the right answer. You see how those are all working together? And here's where I call the original function down here in main. I don't have to talk about square, I don't have to talk about add. It's just being used in the implementation of the function. So now I can give 3 and actually get back an answer that, oh gosh, that does not yet look correct, does it? Was 3 the answer? Or sorry, 14? Okay, yeah, I'm just crazy. 14 is the right answer. Cool. Yay, but if it wasn't, we would debug, we would print and see what was wrong. It gets big quickly. 385, all the sum of squares and numbers from 1 to 10, it seems. So that was breaking down a problem. One function call in main that calls this, who itself calls this and this. Everybody's helping out each other. See that? Alright, that was fun. So that was sum squares from 1 to 2. Let me show you just the standard way in C++ at least of writing our functions in a way that makes our program readable. Okay? There is actually a way to say that a function exists without giving its implementation yet. Just like you can declare a variable before you actually give it a value, you can declare a function before you actually implement it. Just say that it exists and not have anybody need to look at it just yet. Okay? So that is actually really helpful, and that's something you can do. You can declare functions above main and define them below main, because just you as the programmer, not whoever you give your code to, needs to care about the implementations, right? They can just say, oh, okay, I understand this function exists. Like, this is the library, the foo library. I can just call it and assume it gives back the right answer without having to like look at the nitty-gritty details of the function. So here is the declaration. It's just everything but the brace. Put a semicolon instead. That's the declaration, and then here's the implementation. And so you can like sweep them under the rug below main, somewhere that takes like more time to scroll to, but you don't really have to look at it if you're just giving your code to somebody else, okay? They just need to know how to call your function, and that is just part of the definition, the declaration, okay? So let's stay in the same file. Let's do it. Let's move all these down. Oh, sorry, I don't want to copy, I want to cut. So there. So now all these are below main, and it does have to be in order, so I do have to declare them up above. I can do it like this, because otherwise it was complaining about not knowing what this function is right here. It's like, I don't know what that is yet because you haven't declared it. It's defined below, but C++ reads a file in order. There we go. These are function declarations. They're all you need to know how to call the function. Assuming you trust who made them to do the right thing. As a user of this library, you don't care about the implementation, you just care about how to call it, and the declaration is all you need to see. Okay? So essentially we're using a sum of squares from 1-2 library right now. And we could just pretend we don't know anything about the implementation down here. Okay, hopefully that makes sense. It's still the same program, it's just a cleaner way of writing the code. Because the thing that we care about is the names of the functions, and then the main function that's using them, okay? The implementation details of those functions, we don't really want to highlight at the very top of the file, if that makes sense. Okay, so that is the end of my breaking down problems section. Please yell at me if you have any questions about this stuff, but this is a good strategy, okay? So break down into a bunch of different functions to do different things, to solve smaller pieces of the problem, and then bring them together and have them all work together to solve that problem. So you made a bunch of functions, and then declare them above main, implement them below main. That's a good common strategy, and it makes your code look clean. Okay? That is that. And then I think the final thing that I want to talk about today is testing. How can we test our functions to gain some confidence that they're actually doing the right thing? Okay? So let's see how to do that. How do we know when our function that we're writing is correct? Okay? That's what we would like to know. Because, I mean, it'd be really, really nice to know that our function is always going to work, no matter what input we give to it, right? That is beautiful. That is the end goal. Well, it is possible for some function. There's only like a few billion integers, and our computer's pretty fast, so we can just try every possibility of the, I guess, square function, of the add function, for example, and just make sure that it always gives back the right answer. With enough time, we could handwrite all the correct values, run it in our head. That's totally possible. We could do that and gain 100% confidence, right? But most of the time, that's just not feasible. So how can we make it feasible? How can we gain confidence about our function without going to these lengths? Because they're not usually possible, okay? One way is to wait until CSCI 26, where I'll teach you about how to really prove that a function is always correct no matter the input, even if there's like a bunch of ints to consider. You don't have to think about all of them. There's a way. Alternatively, the thing that I'm going to teach you now in this class is probably the most common way of answering this question. It's not like, I call it a middle of the road approach, because it's not like set in stone that your function is correct if it passes all these tests that I'm about to teach you how to write, but you can at least be pretty confident that it's doing the right thing most of the time, okay? So we're going to write a bunch of things called unit tests, okay? That is one very, very common way, probably the most common way in industry, of testing your code and making sure that it's doing the right thing. Okay? So what in the world is unit testing? The idea with that is you take a small piece of your program at a time and you test just that. Okay? Usually it's a function. You're testing a single function at a time. You're not really testing how they play well with other functions. That's just you test that single function with a bunch of sample arguments and that you know the answer to. Okay? So you write a bunch of test cases just for that little chunk, and then you test each individual chunk, and usually that translates to, well, the whole program's correct in that case. Okay? If that did not make enough sense in words, let me show this to you in code. So let's write a factorial function that calculates the factorial of a number. Like if I ask for factorial of 5, it needs to return back whatever the factorial of 5 is. Like 5 factorial is it's supposed to be all the numbers multiplied together, right? 5 times 4 times 3 times 2 times 1, which I think is like 120 or something, but don't quote me there. We'll figure that out together, okay? So let's first make the function at least. What is the return type of the factorial function? What should that be? It should give back an int, right? Because it's multiplying a bunch of ints. Are there any parameters to our factorial function? Well, yes, there is one of them. What are the types of each parameter? Well, I want the factorial of a number. It's always a whole number, right? So it's going to be an int. So it takes an int, returns an int. And then I guess we'll have the name be factorial, right? You can have it be fact for short if you really wanted it to, but we'll just spell it out. And then, once we know all this, we are ready to make a stub, because we have everything that's needed. We don't have the implementation yet, but this is good enough. So, int factorial returns an int, takes an int, factorial of some number n, and it can return 42. Who cares? It's a stub, okay? So, cout, enter number. Now let's see. Let's not enter a number right now, because I'm going to make test cases in a second, but let's just pretend to try the factorial of 5 right now. And of course, the answer is going to be 42 right now. Yay. But what is the real factorial of 5? 5 times 4 times 3 times 2 times 1. Oh, okay, cool. It is 120. So here, let's do this. 120. Is it a correct function implementation yet? No, but we'll get there. So this is just a stub right now. All right, let's make test cases now. Here's what a test case involves. So a test case is a Boolean expression. You're writing essentially a short little if statement that compares what you expect with what you got. Okay, so we'll do that with an if statement and then translate that to the more industry standard assert true function call. We'll implement it together, don't worry. And then we'll make some more tests. So let's make a test case that checks whether we're doing 5 factorial correctly. Okay? Here's a test case. Instead of calling factorial of 5, let's test and make sure that it got back the right answer. Okay? So if factorial of 5 is equal to 120, then we can be like cout passed factorial of 5. That's our test. Otherwise, we can say fails, right? In all caps, usually, because we're yelling at the person. So look at us. Go us. We have a passed test. Yay. And I forgot a new line. Sorry. You see how that's working? You're just checking. You're comparing what you got, which is going to be replacing this call, with what you're expecting, our hard-coded value of 120. Okay? Let's also make a test case for factorial of 4, right? Oops. What should factorial of 4 be? It's 4 factorial equals 4 times 3 times 2 times 1, 1224. Okay, that's useful. And remember that Boolean expression is just what we're putting here. This is something that becomes true or false. Yeah? Something let's say that results in true or false. Because then we're comparing, like if it was correct, we'd get back true, right? If it was wrong, we get back false, and we run the else case. So this was 24. And obviously, we're going to fail this test right now with our stub function. Oops. That's always returning 120 right now. Yay, so we pass one, fail the other. And, again, I forgot a new line. Yay. So, let's translate this into the better version. It's called assert true, okay? Let's make an assert true function. And this is going to encapsulate our test cases. So this is the standard way of doing it. It's void assert true, and it takes a boolean, and it takes a string usually as well. It's like a description of the test, like factorial of 5, factorial of 4. And it holds this kind of if statement. It's like, okay, if your Boolean expression gave back true, then we pass the test. We'll just say B. If B is true, which is equivalent to just saying if B, right? So if B is true, then we passed, and I have no clue the name of the test, but you put that in the description, right? And otherwise you failed. Okay, see how we're going to do that then? And so now this can just become assert true, that all of this that's our condition, and then our description is factorial of 5. That describes the test, right? So that one becomes that, and then the other one becomes this, and that was factorial of 4. And so this is usually how your test cases work. It's you call assert true with a given Boolean expression that computes true or false, and then just the description of that test. So that's used when it prints out the answer, whether you passed or you failed. And so we wanted to see passed we want to see passed everywhere, of course. There's many more tests that we could write, just like assert true that the factorial of 1 is 1. Plenty more places to do stuff. And this is how you write test cases. Does that make enough sense? Let's just try a bunch of possibilities, be as thorough as possible. We'll talk about how we cover the code once I write the real code, and then we'll get a factorial function. Once we start passing all our nice thorough tests, we'll have a factorial function that we actually have some trust in, yeah? So let's go now and let's fix the factorial function. Let's try and make it right. Alright, so let's delete that definitely. So in order to compute the factorial of a number, we have to, well, iterate through all the numbers between 1 and n and multiply them into some variable. I think that is the standard way of doing it. So like int, let's say result starts at 1, and let's now iterate through all the numbers between, I don't know, 1 and n. And add, or not add, result equals result times I. We're going to multiply in, okay? And then by the time this loop is done, we are going to return the value of result. That will give us, in theory, the factorial. So let's take a look at that and see if it's going to give us the right answer. Dun, dun. So it looks like we're passing our tests, yay! So let's now go back to talking about thoroughness. All right? So usually we want to make sure that we're trying every different possible kind of input, even the ones that might cause our code to do weird stuff. When the standard term for covering the standard term for trying all the possibilities and making sure your code works no matter what's going on, no matter what the code might do, that's called covering the code. We want to make sure it always gets run. We want to hit the loop a few times, things like that. Maybe let's try the cases that don't hit the loop. Are there any cases like that? What are some things that we've missed? Like, what's the factorial of, I don't know, the factorial of 0? What should that return? It's supposed to be 1. In math, it's defined as 1. What should be the factorial of -1? That's undefined, right? should we give back something? Maybe we should give back some special answer in that case, like -1, some invalid answer. You see that? That is the kind of thing we have to think about when we make our tests, and that will help us write the correct version of the function too. Isn't that neat? So let's keep going, because which ones don't pass? I'm sorry, this is factorial of 0. But just by virtue of having this loop not run, because I starts at 1 and that's not 0, in this case, we do return 1 already, so that's good. In the -1 case, though, maybe that's the special case, any negative number, we should just return -1 to mean that it's an invalid answer. That's not something we're doing right now, so maybe we should check that. We could be like, if n is less than 0, maybe we should always be returning -1. So this is a edge case, right? When you're incorrectly calling factorial. The other ones should run the rest of the real code. Yeah? And hopefully you saw how, like, us thinking of enough test cases, all the ways that it could go right or wrong, gave us the final right answer. Isn't that neat? So that is testing stuff in a nutshell, and hopefully that makes enough sense. So assert true, very powerful, very useful. Okay? So now I want you to try some stuff. Take a look at this function, and I claim that there is something wrong with it. It's supposed to square the number that you give it. See if you can write a test case to make it work. So let's try this. So test cases are just you running the code in your head and making sure it gives back the right answer, right? So square of 1 is 1 squared, right? Does that give back the right answer? That gives back 1 right now because it's returning x. You see the problem, right? And then square of 2, that gives back right now, gives back just 2 because it's not doing anything with x. It's just giving x back. Uh-oh. So this one passes. This one is incorrect. 2 is not right. It should have been 4. 2 squared is 4. So that can be our test. We'll say assert true. That will force somebody to fix this, right? Assert true that when you call square, and I'll use colors, so I'll fill that in with 2, make sure that's equal to the right answer of 4, and like test 1 or something. We can just call this some description. Oops, I did not want to check that. I just wanted to go to green. So square of 2 is 4. That's test 1. Okay? That is the idea. That's how you can write a test case that makes it very clear what about this is wrong, right? Only one test case was needed to exhibit the issue. And hopefully the program will notice once they see this test failing. Okay? So that's the kind of strategy. Okay, here's a new one. Try this one too. So see what's wrong with it, and see if you can write a test case for it. Alright, what was the issue? It was, well, if you program it out, I think you'll see this is supposed to return the square of a double, right? So is it always going to do that properly is the real question. You can give doubles now instead of just whole numbers. So if you give a whole number, 2.0, that will correctly give you back 4. But the issue happens, right, when you give some number like square of 2.5. What's that going to give back? So the right answer is 6.25. But look at what's happening with squared number. The squared number, I'll just say squared num up here. That variable, what's its type? It's an int, so it's computing 6.25 and then chopping off the 0.25. Oh no. It's trying to put 6.25 in here, but it's only getting the 6 because it's an int. Oh man. So it's going to return 6, or 6.0, which is of course wrong. So again, what is our assert true gonna be? How are we going to exhibit this problem? How are we going to write a test that fails that will work when we fix it? Assert true square of It's going to be 2.5. I'll write that in green again. It's supposed to be 6.25, or really we should be using that absolute value difference kind of equality, but this will be test 2. I'll just be lazy. Really, you should be doing the double kind of equality, the kind that I talked about before. But we'll just say square root of 2.5 is equal to, well, it should be, giving back 6.25. Okay? Actually, equality should work for this particular double, but that's not always guaranteed. Okay, so that's another test. So right now it fails, but if we were to fix this, if this were to become a double variable, then it would pass, and then we'll feel more confident about our function. Okay? So that is officially everything that I want to talk about today, just intro to functions and getting our feet wet with them. We'll come back next time and go in more depth about like how functions work, how they're really getting called. I kind of swept a lot of that under the rug. I was just like, okay, when we call a function, where was that? I said things like, I know it's here somewhere. I said like, okay, the parameters get passed, the parameters in the definition receive arguments in the call, and then once the function call completes, it just goes back and runs the rest of the code, like this calls assert true, then it comes back and calls this one. How does it know how to do all that? We'll talk about that next time, okay? So that will be our one and only lecture for the week on a new topic, and I will see you next week.